Hi children, welcome to another chemistry class. In this session, we are discussing organic chemistry. 12th standard topic, organic chemistry. As all of you know, the first organic chapter in the 12th standard. Haloalkane, haloarene. That is what we are going to discuss in this class. Okay, right. So the chapter is haloalkane, haloarene, the so-called alkyl halides and aryl halides. Haloalkanes, also called alkyl halides. Alkyl halides, all of you know, represented by RX. R for the alkyl group and X for halogen, fluorine, chlorine, bromine, iodine. All of you know that. So X stands for fluorine, chlorine, bromine, and iodine. And I don't have to tell you, normally when we talk about halides, normally when we talk about the general halogen compounds, it is taking chlorine, bromine into consideration. So generally when we talk about the reactions and properties, it is mainly dealing with the alkyl chloride, alkyl bromide, which are the typical members from the family, right? Because alkyl fluorides, many times some abnormal characteristics, alkyl iodides also, fluorides and iodides will be slightly different in their properties. Of course, they are also coming into the picture quite frequently, right? And R means alkyl group, right? While the next one is aryl halides. Aryl halides, all of you know, it is ARX. ARX means, like say, AR means arene, benzene with the X. X again stands for fluorine, chlorine, bromine, iodine. So one is haloalkane, one is haloarene. For example, this is CH3Br. And I don't have to tell you, all of you know, here the carbon is sp3 hybridized in nature. In aliphatic compounds, in alkyl halides, carbon is sp3 hybridized in nature, and the halogen atom is replacing one or more of the hydrogen atom. So it is going to be tetrahedral geometry, and imagine 3 hydrogen atom. In fact, 4th hydrogen was replaced by bromine, and the carbon is sp3 hybridized and maintaining tetrahedral geometry, right? Coming to aryl halides, there is a significant difference. All of you know this carbon is sp2 hybridized in nature. So in aliphatic compounds, alkyl halides, halogen is connected to sp3 carbon, while in aryl halides, halogen is connected to sp2 carbon. That makes a lot of differences in their properties, chemical reactions, and characteristics, right? These are the two class of compounds that we are going to discuss in detail in the chapter, right? As every time we used to comment, we need to go through the nook and corner of the NCERT, including there can be some questions from the introduction paragraph. As we know, the introduction paragraph for the haloalkanes, when you go through, there can be some potential questions, like maybe some references regarding the importance of compounds, right? For example, you see there is a talk on an antibiotic, chlorine containing antibiotic, chloramphenicol, a reference in the textbook. So you must try to put some of the effort to identify what is the nature of that molecule, something like that. For example, if you take the structure of chloramphenicol, this is chloramphenicol structure. This is chloramphenicol structure. This is a chlorine containing antibiotic, chloramphenicol. Right? In the recent examinations, there was questions connecting chloramphenicol, as we are discussing in the chapter content, but that chapter gone deleted. All of you know, the chemistry in everyday life, that chapter is dealing with drugs and molecules related, where chloramphenicol is dealt in the syllabus content, but that gone deleted. But still that molecule is referred in some other part of the chapters where the topic is not deleted. So we have to be little more vigilant on that content. You see, this is chloramphenicol. There is a benzene ring, and there is a nitrobenzene group, and there is two OH group, and one secondary amine group, and two chlorine are available. And in fact, it is not amine, it is amide. I made a wrong measure. It is amide, secondary amide group is there, and there is two chlorine is there, two OH group is there, and there are two chiral centers. This is one chiral center, and this is the second chiral center. So it is always advisable, some of the molecules like this referred in the textbook, we put some effort to see what the characteristics of that molecule is. Because that molecule, when it comes in front of us, we never feel like an unfamiliarity. That is the point. Okay. Similarly, there is another molecule. You see, iodine containing hormone. That is a popular one, thyroxine, the deficiency of which causes goiter. This is thyroxine, iodine containing hormone. How many iodine? There is one iodine here, two iodine, three, four iodine atoms are there. In fact, it is a alpha amino acid. You see, it is carboxylic acid, alpha position, there is amino group. It is alpha amino acid. There is COC linkage between the two benzene ring, and in fact it contains a phenol group. Just to keep in mind the characteristics of that molecule, just to be familiarized, because when you find such a molecule for the first time in an examination hall, it may be something, right? So try to be familiar with the molecule and just the characteristics concerned. That is an iodine containing hormone, thyroxine, referred in the textbook, the deficiency of which causes goiter. And there is some synthetic halogen compound, chloroquine, used for the treatment of malaria. Chloroquine, another molecule, and this is chloroquine, another molecule, which contain a benzene ring, chlorobenzene ring connected to pyridine ring, chloroquine, that is chloroquine, containing a secondary amino group as well as a tertiary amino group. There is a secondary amino group as well as a tertiary amino group, chloroquine. Chloroquines belong to a class of molecules, quine compounds, paraquine, chloroquine, primaquine, anti-malarial drugs, very popular drugs, right? Chloroquines. Then there is a talk on halothane used as anesthetic during surgery. Halothane, a very simple molecule, this is halothane. What is the IUPAC name of halothane? Let us try to figure out the IUPAC name of halothane. This is carbon and this is also carbon, which will get the carbon number 1. Since there are 3 fluorine atoms, we can give 1, 2. Correct, no? Isn't it? Yes, it is 1, 1, 1, 2, 2. And the molecule is 2 bromo, 2 chloro, 1, 1, 1 trifluoroethane. Right? Since it is a simple molecule, isn't there is a chance of asking IUPAC name? And the molecule is referred in the, maybe in the introduction pages, but there is in the NCERT. So give due importance, because that can be a simple direct question. And what is the name? Let me repeat. This is 1, this is 2, because there are 3 fluorine, 1, 1, 1, 2, 2, like that, lowest locate. While in the naming, preference goes to alphabetical order. So 2 bromo, 2 chloro, 1, 1, 1 trifluoroethane. That is the very famous anesthetic chemical halothane, a simple molecule explained in the introduction paragraph, and of course the few other molecules also, and you are advised to get familiar with that. And next part of the chapter, entering into the classification of halogen compounds. As I was explaining earlier, aliphatic, haloalkane, haloarene, as I was explaining earlier, alkyl halide, aryl halide. That is the simplest two important category, aliphatic and aromatic. There are so much other classifications are also coming in the due course of the chapter. and that is also an important point of discussion. Like alkyl halide represented as Rx, aryl halide represented as ARX, right? Now, when you talk about CH3Cl, that is a monohalogen derivative, it can be CH2Cl2 dihalogen derivative, it can be CHCl3 trihalogen derivative, the very famous compound all of you know, chloroform, and CCl4, the entire hydrogen atom replaced by chlorine, carbon tetrachloride or tetrachloromethane. So this is one hydrogen replaced by chlorine, two hydrogen replaced by chlorine, three hydrogen replaced by chlorine, all hydrogen atom replaced by chlorine. So when in a hydrocarbon all hydrogen atom replaced by chlorine, it is also known with another class of compound, perhalogen derivative. Such molecules are called a perhalogen derivative. Some of the perhalogen derivatives can use it as a potential substitute as blood during surgery. Some of the perhalogen derivatives, right? So that is about monochloro, dichloro, trichloro, polychloro, polyhalogen derivatives. Polyhalogen derivatives, some of the compounds are very famous, like chloroform, like iodoform, XI-XII iodoform. They are all famous, popular compounds. Okay, so that is one category. So based on the number of halogen atoms, we can have a category. Based on whether aliphatic group or aromatic group connected, we have alkyl halide and aryl halide. Based on number of halogen atom, we have one category. Based on the type of carbon to which halogen connected. For example, whether it is halogen connected to primary carbon, secondary carbon, tertiary carbon. We can have three types. All of you know CH3, CH2Cl, chlorine connected to primary carbon. Primary carbon means one carbon connected to next another one carbon. That is primary carbon. So halogen bonded to primary carbon, primary halide. Halogen connected to secondary carbon, CH3, CH, CH3. Here you can see the halogen, say for example bromine, connected to secondary carbon. That is a secondary halide. All of you know this. I am just reminding you. While tertiary halide, CH3, CH3, CH3Br. That is a tertiary halide. The halogen atom connected to a tertiary carbon, tertiary halide. Right? So based on to which type of carbon halogen is connected, we can have primary, secondary, tertiary. So alkyl halides, aryl halides, monohalogen, dihalogen, trihalogen, polyhalogen, perhalogen. Right? Then primary, secondary, tertiary. Another important class of compound that also maybe many of you remember, vinyl halides. Vinyl halides. What is a vinyl halide? Vinyl chloride, CH2 double bond CHCl. The halogen atom connected to an sp2 carbon. That is a vinyl halide. But it is different from aryl. Aryl means a benzene ring we consider. This is not a benzene ring. But halogen is connected to an sp2 carbon. This carbon is sp2 carbon, all of you know. And halogen atom connected to that sp2 carbon. That is vinyl halide. This is a very popular compound, vinyl chloride. I don't have to tell you the importance of vinyl chloride. Almost all of you may be aware of the importance of vinyl chloride. Vinyl chloride polymerizes giving PVC. Vinyl chloride polymerizes giving PVC. All of you know polyvinyl chloride, right? There is another class of halide, that is allyl halide. Allyl halide. What is an allyl halide? CH2 double bond CH, CH2Cl. This carbon is called allyl carbon. Allyl carbon is an sp3 carbon next to a double bond. It is an sp3 carbon next to a double bond. Right? So that carbon carrying a halogen, that is called allyl halide, allyl chloride. This is allyl chloride. So when the chlorine atom directly connected to the sp2 carbon, that is vinyl, while the chlorine atom connected very next to a double bond sp3 carbon, that is called allyl halide. Just for example, if you take a molecule like this, say cyclohexene, you see cyclohexene, imagine chlorine is connected to this carbon or bromine connected to this carbon. This will be vinyl in nature, vinyl in nature, as the halogen connected to sp2 carbon. This is sp2 carbon. Meanwhile, if the halogen is connected to this carbon is called a allyl carbon. This is sp3 carbon which comes next to a double bond, right? So sp3 carbon connected to a double bond is called a allyl carbon, in which a halogen coming allyl halide. So vinyl halide, allyl halide, alkyl halide, aryl halide, monohalogen, dihalogen, polyhalogen, primary, secondary, tertiary. Various categorization of halogen compounds is one of the most important topic from the initial segment of the chapter. And even you may be asked to identify which category of the molecule belong to is. The given compound belong to which category of molecule. You may be asked to identify. So get familiarized with that. Another very important class of compound is benzyl halide. Benzyl halide. What is a benzyl halide? Benzyl halide. This is benzyl halide. This is the benzene compound, and this carbon is called benzyl carbon. This carbon is called benzyl carbon. The carbon connected to the benzene ring is called a benzyl carbon, and benzyl carbon carrying a halogen, that is called a benzyl carbon. Now when you take benzyl halide, when you take allyl halide, in all these cases you can have primary, secondary, tertiary. This is primary benzylic. Primary benzylic. Imagine there is a branching coming here, then secondary benzylic. So benzylic can be primary, secondary, tertiary. Allylic can be primary, secondary, tertiary. So all these category of molecules which belong to halogen derivatives, try to familiarize, and that in fact is an important part of the introduction segment of the chapter. Okay. Of course, I don't have to tell you the naming part. The naming part is also important. You are supposed to practice as many names as possible. As many names as possible, particularly all examples in the textbook NCERT. And of course, we are feeding with a whole lot of examples through our materials and classes, right? And that's a part of the initial segment, the nomenclature part of the organic chemistry. That is some basic principles of chemistry related nomenclature part. Like the compounds, common name as well as IUPAC name. N-propyl bromide, isopropyl bromide, isobutyl chloride, bromobenzene, meta. See, why we are insisting to go through the examples in the NCERT. You can see the molecule given here. Sim tribromobenzene. Sim means symmetrical. Symmetrical tribromobenzene. So such a terms, be familiar with the examples given in the textbook. Symmetrical. What is symmetrical? 1, 3, 5. That is symmetrical. 1, 3, 5. That is symmetrical. This is not symmetrical. So 1, 3, 5. Tribromobenzene. Symmetrical. This is N-propyl group, and this is isopropyl group, and this is isobutyl group, like that. And this is neopentyl group, you know, neopentyl group. And the molecule will be neopentyl chloride. Neopentyl chloride. IUPAC name is 1, 2, 3. 1 chloro, 2, 2-dimethyl propane. 1 chloro, 2, 2-dimethyl propane. Like that. Okay. So not only in this chapter, every organic chapter, I don't have to tell you, Now, practicing the nomenclature, that will be an important segment of the introductory portion of every chapter. How to take up as many examples as possible. Just to try to solve all the exercise and textual questions given in the NCERT. And try to solve all the feeding that we are giving from our side as extra and related similar molecules. Okay. Yeah, I forgot to tell you very important another class of compound, gem dihalide and vis dihalide. Gem dihalide and vis dihalide. Two halogen coming on the same carbon atom. That is called geminal. Geminal means gem dihalide. On the same carbon atom, when two halogens are coming, it is called gem dihalide. Not two, three can also be. So, more than one halogen atom coming on the same carbon, that is called geminal. While on the nearby carbon, it is called vicinal. Vicinal means on the near vicinity. So, 1,1-dichloroethane, that is called ethylidene chloride. 1,1-dichloroethane called ethylidene. Ethylidene. That term ethylidene, that refers gem. So, ethylidene chloride, that's a gem dihalide, 1,1-dichloroethane. While this is ethylene dichloride, vicinal, 1,2-dichloroethane. This is 1,1, that is 1,2. That is another category of molecule, right? Try to establish a test, a simple test with which you can distinguish the two molecules. Try to establish. I am just putting a question in front of you. Just try to establish simple test, simple chemical test to distinguish between the geminal and vicinal dichloride, especially gem dichloride, ethylidene chloride and ethylene dichloride. How simple test you can provide to distinguish these two molecules? Think about it. Okay, and just placing a question in front of you. There are some tabulated examples are given. This is vinyl chloride, this is allyl bromide, this is dichloro, trichloro, tribromo, tetrafluor, tetrachloro. And some of the examples given like this, you must try. For example, this molecule, how we can identify the IUPAC nomenclature of this molecule. As the way the molecule is drawn, sometimes it may be a bit confusing, but very simple to solve. You can do it like this: CH3, CH double bond, C, CH3, single bond, CH, CH3. See, if this molecular condition, if just to create some sort of confusion, put it in the right way, in the condensed format which we generally familiarize with, the CH3, CH, double bond, CCS3, single bond, CHBr, CS3. Right? Now, what is a long chain? No doubt, this is the long chain, isn't it? Now, from where we need to number, this side or that side? Is the numbering to be done from left or right? From where we do the numbering? From this side or that side? 1, 2. 1, 2, 3. The privilege go to double bond. So, it is 1, 2, 3, 4, 5. So, the name will be 4-bromo. 4-bromo. 3-methyl. 3-methyl pent 2-ene. That is the compound. 4-bromo, 3-methyl, 4-bromo, 3-methyl pent 2-ene. Why we are numbering from the left side? There is a methyl group, there is a bromine, and there is a double bond. Priority will be for double bond. When there is a halogen and a double bond gets the priority. When there is a OH and a double bond, OH gets the priority. Please understand. Don't forget. Yes. So, considering the priorities, we can understand the numbering from this side and we get the compound 4-bromo-3-methyl pent-2-ene, right? So such exercises, where is the compound? Where is the compound? We took third one, 4-bromo-3-methyl pent-2-ene. Practice. Okay. That's about the classification of halogen compounds. And there are, in fact, you have many more exercises. I would say two-way exercise is essentially required to expertise yourself from the nomenclature segment. Usually I used to say, when structure is given, try to write the IUPAC name. When the IUPAC name is given, try to give the structure. Do both. Okay. Say for example, if you are dealing with this compound, just try to practice the fifth one. 1-bromo, 4-secondary butyl 2-methyl benzene. So look at the last part of the molecule. You are drawing benzene. I'm drawing benzene. This is benzene. Okay. Now 1-bromo, wherever I give 1, that is wherever I give bromine, that is 1. So this is 1. 1-bromo, 4-secondary butyl. 1, 2, 3, 4. This is 4-secondary butyl. You must know this group is called a secondary butyl group. I have drawn only skeleton, CS3, CH, CS2, CS3. I have drawn only skeleton. Try to understand CS3, CH, CS2, CS3. This is secondary butyl at the 4th position, and 2-methyl. So that's it. 1-bromo, 4-secondary butyl, 2-methyl benzene, and it's over. It's over. So practicing a compound given, trying to write the name, and the name given, try to write the compound. This is essential practice required in every chapter. Every chapter there is introduction segment dealing with isomerism, nomenclature, etc., etc. Try to practice, because that's going to be the question directly we are going to encounter for the competitive examination and of course the board exam also. Okay. Now on to the details of nature of carbon halogen bond. Nature of carbon halogen bond. What is the nature of carbon halogen bond? Very simple to understand. Carbon halogen bond will be sufficiently polar. Carbon halogen bond will be sufficiently polar. If you take this bond, you see there is delta positive on the carbon center, delta negative on the halogen center. Nobody has to tell you. Everybody know that. Halogen being more electronegative will carry a partial negative charge on halogen, quite obviously partial positive charge on carbon. So carbon halogen bond is always polarized like that. There will be a delta minus here and there will be a delta plus here. So this is in fact a electrophilic center. This is a electrophilic center. That is the electrophilic center and highly prone to nucleophilic substitution reactions. That's why haloalkanes are highly prone to nucleophilic substitution reactions. The reactions given by alkyl halides are typically the so-called SN reactions. All of you know that, SN reactions, because of this polarity, right? And we have a tabulated arrangement, I believe, regarding the dipole moment and characteristics of the halogen compounds, and this table I would say it's very important, very important. You see the bond length, fluoride, chloride, bromide, iodide, we are dealing with the monohalogen derivative. Bond length given, bond length quite naturally increases from fluoride to iodide. I don't have to tell you why. Fluoride minimum, chloride, bromide, iodide maximum, just because of the size. Fluorine is small in size, small bond length. Iodine is larger in size, larger bond length. So bond length increases from fluoride to iodide. Naturally, bond enthalpy, when the bond length is increasing, means quite naturally reflecting on the bond enthalpy. Bond enthalpy decreases. Bond enthalpy minimum here and maximum here. 450 range here, 230 range here. So 450, 350, 300, 230 range. That is the kind of bond enthalpy kilojoule per mole coming for fluoride, chloride, bromide, iodide. It's not quite surprisingly, iodine is a better leaving group. Iodine is a better leaving group which will break fast. This will break fast. Iodine is a better leaving group, and one important point is bond enthalpy. Ri bond enthalpy is minimum. And this is something very interesting to see. The dipole moment, it is most expected for fluorine because of its high electronegativity, but the value is slightly greater maximum for monochloro derivative. Monochloro derivative found to be slightly upper hand for the dipole moment. So this is having 1.86, this is having 1.847. While the others are lower, 1.83, 1.63, like that. So there is something important to be noted regarding the dipole moment. It is not monomethyl fluoride, rather it is methyl chloride. Greater dipole moment than methyl fluoride, even though marginally, right? That's about the characteristics of bond, characteristics of carbon halogen bond in alkyl halide. And our next topic is methods of preparation of haloalkanes. Methods of preparation of haloalkanes. Methods of preparation of haloalkanes. See the first method from alcohols. Alcohols can be easily converted to haloalkanes. Okay. So there are few important reactions which are enlisted in the textbook, which you need to particularly look at each and one every reaction and the specific features related to each and every reaction. You can see certain listed reactions. Number 1, alcohol treated with HCl and anhydrous zinc chloride. Alcohol treated with concentrated HCl with anhydrous zinc chloride. In fact, the anhydrous zinc chloride is acting as a catalyst which will help to break the carbon oxygen bond, and the reaction will be a substitution reaction. OH group will be replaced by chlorine. OH group will be replaced by chlorine. For example, CH3, CH2OH when treated with HCl and anhydrous zinc chloride. Upon heating, you can find this OH group will be replaced by chlorine. You get a CH3, CH2, Cl. You will get a white turbidity. In fact, this reaction has got some importance. It can also be used for detecting the primary, secondary, tertiary alcohols. One of the very popular tests you may be aware of, Lucas test. Lucas test. See, the reaction concerned is otherwise called a Gauss process, converting alcohol to alkyl halide using HCl. It is called a Gauss process. The reaction as such may be called as Gauss process. But the same reaction when used for testing alcohols, primary, secondary, tertiary alcohols, can be tested using anhydrous zinc chloride and concentrated HCl, which is so called a Lucas reagent, and the test is called a Lucas test. This is the reaction behind that, because the order of reactivity in fact is used here. The order of reactivity of alcohols, all of you may be aware of, the order comes as tertiary greater than secondary greater than primary. This is the order of reactivity of alcohol towards all these substitution reactions. A tertiary alcohol easily getting substituted, right? So this can be used as a test for the primary, secondary, tertiary alcohol. Imagine you have 3 test tubes given containing primary, secondary, tertiary alcohols. Okay, but we don't know which test tube contain primary, which contain secondary, which contain tertiary. You can have easy test with a Lucas reagent, the so-called HCl and anhydrous zinc chloride. It can be used as a reagent added to the first test tube. You see that nothing happens. Okay, then we are adding to second test tube the same Lucas reagent. We see that nothing happens. And upon adding the Lucas reagent onto the third test tube, you get an immediate turbidity. The immediate turbidity obtained is a clear indication that the reaction is quite instantaneous, which is given by tertiary alcohol. And what is the cause of turbidity? An alcohol treated with the HCl in presence of anhydrous zinc chloride, you are getting RCl plus H2O. In aqueous medium, RCl will be precipitating. That is actually obtained as a turbidity. So tertiary alcohol provide a immediate turbidity. While secondary alcohol, you may get a turbidity only after 5 to 10 minutes. So after 5 to 10 minutes, if you get a turbidity, you can confirm this is a tertiary alcohol. I mean immediate turbidity, tertiary alcohol. After 5 to 10 minutes, this will be a secondary alcohol. Because quite natural, look at the reactivity. This is the reactivity. So tertiary, most reactive, then secondary, while you don't get a turbidity in primary alcohol under normal condition unless you heat it. Only by heating you get a turbidity there. This is a convenient, simple test for simple alcohols. Remember, this test may not be applied for bigger alcohols. For bigger alcohols containing some 8 carbon atom, 10 carbon atom, 15 carbon atom, bigger alcohols, this may not be a convenient test. For simple alcohols, this can be taken as a comfortable test for identifying is it a primary alcohol, secondary alcohol, tertiary alcohol, known after Professor Luca of California University. Okay, that is Luca's test. In fact, Luca's test is not the matter of point we are discussing here. We are discussing here the preparation of haloalkane. I was just explaining on the course of study. This process I was explaining in detail. This process, which is known as Grau's process, which is part and parcel of Luca's test also. Look at the second reaction, alcohol treated with the NaBr sulfuric acid. Alcohol treated with the NaBr sulfuric acid, you have been able to get a RBr. There is a similar reaction not quoted here, but you can see it is commented over the text. Good yield of alkyl iodide may be obtained by heating alcohol with sodium or potassium iodide in 95% orthophosphoric acid. So alcohol treated with NaI or Ki with H3PO4, you can get Ri. Quite naturally, we know the preparation of alkyl fluoride and iodides will be discussed somewhat in an abnormal manner. Normally, when we talk about halides, it is chlorides, bromides. There will be some sort of changes in the preparation and properties of fluorides and iodides. Already, I have commented on this matter, right? All of you know that also. One more point given. Constant boiling with the HBr 48%, you get alkyl bromide. That is another possibility apart from this reaction. So this reaction we have gone through in detail, and this reaction also. Look at the third one. Next reaction. That is with the PX3. What is PX3? It can be PCl3 or PBr3. PCl3 or PBr3, alcohol reacting with the PCl3 or PBr3, you will be getting Rx and H3PO3. You get phosphorus acid producing alkyl chloride or bromide. PCl3 or PBr3 interacting with the alcohol. You get alkyl chloride or bromide plus H3PO3, phosphorus acid. Then there is a reaction with the PCl5. PCl5 reaction will be again, all these cases what we find is OH group is getting substituted. The OH group is substituted by a halogen, right? So this OH group is substituted by chlorine. A slight difference from the reaction between PCl3 and PCl5. Definitely you must make a note on to it. Here you get Rx plus H3PO3, while here we are getting RCl with the POCl3 and HCl. Right? You have to recollect the way PCl3 and PCl5 hydrolysis, I don't know how many of you are aware of. PCl3 hydrolysis will be a unique type of reaction, while PCl5 is not. I'm putting that question in front of you. You may please think and identify, and that will lead you to a knowledge why these two reactions are different here. PCl3 and PCl5. What is the kind of hydrolysis they perform? I'm putting that question in front of you. You please investigate and find out. There is a difference in the hydrolysis of PCl3 and PCl5. PCl3 give a continuous unique type of hydrolysis reaction, while PCl5 undergo two-step different type of hydrolysis. Why and how that happens? Why that happens? How that happens? Why that happens? That you need to learn. Try to get a picture on that, and then come back and revisit on these two reactions and try to understand how these two reactions are different on the course of reaction with the PCl3 and PCl5, how they differ. Okay, that question I am putting in front of you. This you need to review the hydrolysis of PCl3 and hydrolysis of PCl5. What is the difference? How is the different? And what is the cause of that difference? Try to investigate. Okay. Next one, again alcohol treated with the red phosphorus and halogen. Here halogen means bromine iodine. Please understand, PBr3 is not that much stable. PBr3, in fact PI3, it is not that much stable. They are produced in situ by mixing red phosphorus with the halogen. When you mix red phosphorus with the halogen, you can get a PBr3, PI3, which are produced at the moment of the reaction, and they can replace OH group with the X. X means here bromine or iodine. And the last reaction, one of the very important reaction, alcohol treated with the SOCl2. What is the name of SOCl2? All of you know that. Thionyl chloride. Thionyl chloride. ROH treated with the SOCl2. Thionyl chloride. You get RCl producing SO2 and HCl. I'm sure you might have noticed SO2 is a gas which escape and HCl is a gas which escape. The byproducts are gases, and that's why this is the most wanted reaction or most advisable reaction in the laboratory. You might have learned this procedure, which is so called Darson's procedure. This is called Darson's procedure. Darson's process, producing alkyl halide with the SOCl2, alcohol treated with the SOCl2, right? And remember, it is only for RCl, not for RBr, not for RI. A similar process is not available for RBr. A similar process is not available for RI. Try to identify why. Why that is not possible? That also you must investigate and find out. I am putting a question in front of you. Why it is not possible to produce RBr or RI with a similar process like RCl you are getting from thionyl chloride? Because this is one of the most important reaction. Why? Because it is most advisable reaction in the laboratory. Because you get the product in the pure form. Why you get the product in the pure form? Because the byproducts are gases and they will escape. So since the byproduct are gases and they escape, we are getting pure product and is most advisable reaction in the laboratory, but we don't get that reaction. Unfortunately, it is available only for RCl, not for RBr and RI. Think about it and try to find out yourself, or definitely we are going to discuss in our classes. Okay. Many of you know, I'm sure, many of you know why the reaction is not available. That is the sequence of reaction available. Preparation of alkyl halide from alcohols. Let me remind you, number one, reaction with HCl, reaction with NaBr sulfuric acid, and reaction with HBr. I told you constant boiling with HBr, and reaction with the KI-NaI with the phosphoric acid. We have gone through. Then reaction with the PX3, reaction with the PCl5, reaction with the red phosphorus, halogen, and finally reaction with the thionyl chloride. What is the order of reactivity of alcohols? Already commented, tertiary greater than secondary greater than primary. Okay, it's one of the most important reaction that we are handling for alcohols converted to alkyl halides. This reaction is not mentioned for aryl halides. This reaction is not mentioned for aryl halides because it's not possible. SN reactions are not favorable for phenols. Aromatic compounds does not favor SN reaction. If you take phenol, don't just think about under ordinary condition this can be converted. OH group may be replaced by chlorine. It is not possible because under ordinary condition a nucleophilic substitution is never promoted for aromatic compounds because it is not possible to have a easy breaking over this bond because due to partial double bond character, there are multiple reasons. One important reason we comment is a partial double bond character between the carbon and the leaving atom, which is creating and is not easy to break that bond. Here carbon oxygen bond cannot be broken comfortably and thereby substituting with another halogen. That is the issue all of you may be aware of. Next is preparation from hydrocarbons. Preparation from hydrocarbons. Free radical halogenation. A topic well explained or well learned in the chapter hydrocarbons of 11th standard topic. Free radical halogenation reaction. How this chlorine is added to molecules like hydrocarbons, like say for example methane added with the chlorine in presence of light, you are getting CH3Cl plus HCl. This is a free radical substitution reaction. In fact, it is a free radical chain reaction. A detailed study happened already in that chapter. Hope you remember chain initiation, chain propagation, chain termination, like that 3 steps involved. You see, chlorine breaks going for a homolytic cleavage in presence of light. You are getting chlorine free radicals, and that chlorine free radical attacks methane and you get methyl free radical replacing HCl. HCl is out and you get methyl free radical. Now that methyl free radical attack again chlorine molecule, you get CH3Cl, the first product in that sequence. In fact, this is not a reaction which is advisable in the laboratory because it gives a mixture of products. You are getting a mixture of products. And this is a chain reaction. This is a continuous chain reaction producing, in fact, all possible products. You may get a variety of products in this kind of reactions. When I am taking a simple molecule like methane, I am getting CH3Cl, I am getting CH2Cl2, I am getting CHCl3, I am getting CCl4. All possible products are obtained as it is a free radical chain reaction, substitution reaction. This is learned in the 11th standard topic. And the order of reactivity, all of you aware of, it is F2, we never talk about the reaction, it is Cl2, Br2 and I2. These two reactions we never usually talk about. This is the usually referred reaction. Reaction with the chlorine, reaction with the bromine, and that is what usually we refer, particularly chlorine reaction. We don't talk about fluorine reaction, we hardly talk about iodine reaction. Why? Because fluorine is uncontrollably reactive. The reaction with the fluorine is it can react even in darkness. That is it's uncontrollable reaction. While reaction with iodine, it is too slow and reversible. Only with the help of some good oxidizing agents like nitric acid or iodic acid, you can conduct that reaction. With the help of good oxidizing agent, by replacing the product obtained HI, you can conduct that reaction. Otherwise, the reaction is not that much good to experience, right? And what will be the order of attack on hydrocarbon? If you take a bigger hydrocarbon, the order of attack will be a tertiary hydrogen attacked first, then secondary hydrogen, then primary hydrogen. This is the order of replacement happens with the hydrogen. A tertiary hydrogen is replaced first. Then secondary, the order of the rate of reactivity will be tertiary, secondary, primary. The order of reactivity will be fluorine, chlorine, bromine, iodine. Hardly we talk about fluorine, iodine. Normally we are talking about chlorine and bromine. Okay. So that is preparation from hydrocarbons commented. So preparation from alcohols, preparation from hydrocarbon. Number one, free radical halogenation of alkanes. Number two, from alkenes, addition of hydrogen halide, addition of hydrogen halides on alkene. Many of you definitely remember addition of hydrogen halide on alkene we discuss in two contexts. How a symmetrical alkene is added and how an unsymmetrical alkene is added. If you talk about a symmetrical alkene like ethene, this is ethene added with bromine in presence of CCl4. I think all of you remember one bromine added over here, one bromine added over here, and you get vicinal dibromide, CH2Br, CH2Br. You get vicinal dibromide. And there are something special about these reactions. Many of you may be remembering this is a test for unsaturation. The orange-red color of bromine gets decolorized. It's a test for unsaturation. Very important point. It is an anti-addition following a cyclic bromonium ion. In fact, the double bond is polarizing bromine. The double bond is polarizing bromine as minus and plus. And this plus bromine is attacked from one part of the molecule and you get CH2. You get a cyclic bromonium ion formation. Cyclic bromonium ion formation. And this second Br minus is attacking from the opposite side. So one bromine attacking from one side, the other bromine attacking from the opposite side, which is called anti-addition. Anti-addition. So bromination generally is anti-addition. It is a test for unsaturation. These things already learned. And there is nothing more to discuss if you are taking a symmetric alkene like ethene. Ethene added with the bromine, you get only one product. You get only one product and the product is 1,2-dibromoethane. 1,2-dibromoethane. Right? This reaction may be called as halogenation reaction. Halogenation reaction. In fact, I think the caption with which I started is addition of hydrogen halide. Okay, let's see what is the addition of hydrogen halide. This is halogenation reaction. Of course, it is a electrophilic addition reaction, anti-addition, test for unsaturation. The caption with which I started is addition of hydrogen halide. How the hydrogen halide is added? That too is a electrophilic addition reaction. You see this CH2 double bond CH2 added with HBr in darkness. You see hydrogen will be added here and bromine will be added here. You get CH3 single bond CH2Br. Ethyl bromide is added. Ethyl bromide is obtained. It's an addition reaction. What kind of addition reaction? Electrophilic addition reaction, because H plus is added in the rate determining step of the reaction. In the rate determining step of the reaction, the alkene group is influenced by or attacked by or is attacking H plus. It is electrophilic addition reaction. Electrophile is added in the rate determining step. Right? Hope you remember the mechanisms involved. Step 1, it is added with H plus and you get CH3, CH2 plus, you get a carbocation, and this is the rate determining step of the reaction. That is the slow step of the reaction, and hence it is called electrophilic addition reaction. Only in the second step, Br minus is added. On the second step, Br minus is added and you get the final product CH3, CH2, Br. Here is actually what I was about to tell you earlier. When you add HBr to symmetric alkene, there is nothing to talk about. Only one product is obtained. While you add HBr to unsymmetric alkene, hope you remember the story behind involved is you get multiple products, you get two products. For example, if you are taking propene added with HBr, propene added with HBr in darkness, you may find hydrogen comes here and bromine comes here, possibility number one, which is CH3, CH2, CH2Br, that is 1-bromopropane. 1-bromopropane. And now another chance is hydrogen added here and bromine added here. You get a second possible product, that is CH3, CHBr, CH3, that is 2-bromopropane. 2-bromopropane. I'm sure many of you have been able to recollect by the time I started discussing the very popular, the very famous Markovnikov addition. This is what called a Markovnikov addition. According to Markovnikov's rule, the negative part of addendum, this is the positive part and this is the negative part. Negative part of addendum predominantly connected to carbon containing less number of hydrogen atom that we are learning in the 11th standard topic, including the cause of such an attack. That means the detailed mechanism. How the detailed mechanism is explaining the formation of a primary carbocation in one case and secondary carbocation in another case, and the reaction more travel in the secondary carbocation path, and thereby this you get as a major product. This you get as a major product, while this will be only a minor product. Because when H plus is added in the first step, you may get a carbocation over here. And carbocation formed here will be favorable because of greater stability. Order of stability of carbocation is the reason. The order of stability of carbocation, hope you remember, tertiary greater than secondary greater than primary. When the carbocation comes here, it is a primary carbocation, and carbocation comes here, it is a secondary carbocation, and secondary carbocation path will dominate, and there on the C plus Br minus will come, and hence it is a major product. With the detailed mechanism, this fact is explained in the 11th standard topic chapter hydrocarbons. I'm sure all of you remember Markovnikov's rule. Sometimes you might have forgot the mechanism. Please review that mechanism. Markovnikov addition, and don't forget to review anti-Markovnikov addition. Markovnikov addition may be applicable to all compounds like added, like HCl, HBr, HI, water added, sulfuric acid, whichever molecule added across the carbon-carbon double bond. It's happening if it is unsymmetric alkene. It's happening according to Markovnikov addition normally. But when HBr added in presence of peroxides or in presence of light, hope you remember that particular scenario. When you take an unsymmetrical alkene like propene, which is added with HBr in presence of a peroxide or in presence of light or sometimes even heating, you can find the negative part of this Br minus is actually coming on the first carbon, and the major product obtained will be CH3, CH2, CH2Br. You get 1-bromopropane as major product. And this is called anti-Markovnikov addition. Anti-Markovnikov addition. That too, delta in detail regarding why this anti-Markovnikov addition happening, it is explained with the mechanism. And also remember, it is substantially or clearly explained in the classes that it's applicable only for HBr. Anti-Markovnikov of addition applicable only for HBr, only in presence of peroxides, in the presence of light. And the reason behind is, some of you may be remembering the mechanism. It is previous one. Markovnikov addition happens with the carbocation mechanism, while anti-Markovnikov addition happens with the free radical mechanism. There is a change in the story. The thread of the story entirely changes. It's a different story. Markovnikov addition and anti-Markovnikov addition, it's a different story. It is free radical mechanism. And getting a free radical, also the order of stability, tertiary, secondary, primary, when you go through that mechanism, you can find a more preferable attack of Br dot. Bromine free radical, Br dot, happens on this side. Because when bromine is added here, free radical will be forming on this carbon, which is a secondary free radical. And hence that path dominates. Okay, please review that mechanism. Please review that mechanism. It was also dealt in detail in your classes. So when you're dealing with the preparation of haloalkanes, addition of halogenation reaction, you will get a vicinal dihalides, which is a test for unsaturation. It is anti-addition, number one. Number two, reaction with the hydrogen halide. Reaction with the hydrogen halide, you have to review Markovnikov addition and anti-Markovnikov addition. In case of unsymmetric molecules, any molecule added under normal condition, it is Markovnikov addition, while HBr added to unsymmetric alkene only in presence of peroxides or light, it will be opposite product obtained, anti-Markovnikov product is obtained. Right? These all things are actually a review. So that is explained over this region, addition of halogen, all these things we have discussed. And now there is a halogen exchange reaction, a very, very famous popular reaction, halogen exchange reaction. You see, we prepare an alkyl chloride or bromide and treat with NaI in presence of dry acetone. You get Ri obtained, where NaCl will precipitate. See, chlorine or bromine replaced by iodine. Already it was commented a few minutes back. When we talk about the preparation of alkyl halide, generally we are talking about chloride, bromide. Because there is some sort of abnormality involved in fluoride and iodide. So how do you prepare iodide? How do you prepare fluoride? That is what dealt in this segment. You see that we prepare alkyl chloride or bromide. And now this is treated with NaI in dry acetone. NaI in dry acetone. NaI dissolves in dry acetone. And you get I minus effectively. And that is replacing X minus. X minus will be replaced by I minus. And you get Ri and you get NaX. NaX means it can be NaCl or NaBr. This will precipitate in dry acetone. That's a very important point. NaI soluble in dry acetone, while NaCl and NaBr precipitate. That actually facilitates the reaction. That precipitation of NaCl or NaBr in dry acetone is facilitating the reaction according to Le Chatelier's principle. When they are able to come out, this is replaced by iodine. When X, chloride, bromide are able to come out as NaCl or NaBr, they are ready to escape. They are ready to leave the place. They are leaving the particular area, and that area occupied by I minus, and you get Ri. The very famous reaction, Finkelstein reaction. Finkelstein reaction. Yet another nucleophilic substitution reaction. I minus, which is a better nucleophile, replacing chlorine or bromine. And the replacement of chlorine or bromine happens as NaCl or NaBr. They are ready to precipitate in dry acetone. Why so happens? NaI soluble in dry acetone, NaCl, NaBr precipitate in dry acetone. It is because of the greater covalent character of NaI. NaI, iodine being larger in size, hope you remember, according to Fajan's rule, we can comment, it is more covalent in nature and is soluble in organic solvents like dry acetone. While NaCl, NaBr are pretty more ionic, they precipitate in dry acetone. and that actually facilitates the forward reaction replacing X minus, that is Cl minus Br minus replacing with the I minus. A very popular reaction, Finkelstein reaction. A similar reaction we can find with the replacement of chlorine bromine with fluorine. What we do? Alkyl chloride or bromide is treated with metal halides. You see, alkyl chloride or bromide heated with metal fluorides, silver fluoride, mercurous fluoride, cobalt fluoride, antimony fluoride. A metal fluoride heated with alkyl chloride or bromide. You can see that halogen, existing halogen replaced by fluorine, and is a very important commercial process, Schwarz reaction. So replacing a halogen with iodine, Finkelstein reaction, replacing a halogen with fluorine, Schwarz reaction. In Finkelstein reaction, NaI with the dry acetone we are making use of, while Schwarz reaction, a metal fluoride like silver fluoride, antimony fluoride, cobalt fluoride, etc. may be heated with the alkyl chloride or bromide, where chlorine or bromine replaced by fluorine. That is what the reaction. Okay. Now it is the preparation of haloarenes. Preparations of haloarenes.